In this video, we're going to look at categorizing geometric figures. Below are 6 definitions of categories of quadrilaterals. So we're going to look at these 6 definitions, and then we're going to see what categories each of the figures we're given fall into and classify them. So first, let's look at what a quadrilateral is. So notice I have some words highlighted here, and you have to look for specific attributes to make sure that you're deciding whether they fall in the proper categories. So quadrilaterals are closed shapes. Here's an example of a closed shape and a not closed shape. So a closed shape, there's an inside and an outside, and to get from the inside to the outside, you would have to cross a boundary of the figure. Okay. In a shape that's not closed or open, you could see there's an opening. Okay. So there's not really, this seems kind of like the inside, but there's not really an inside or an outside because they're not separated by a boundary. Next, we're told that a quadrilateral, it's in a plane, which is a two-dimensional space like a piece of paper or the screen of your computer, and that it consists of 4 line segments. So here's an example of a line segment, and this is an example of something that's not a line segment. So line segments are by definition straight, okay? And notice we have these endpoints. It ends on both sides of the line segment, so it doesn't continue on forever. We would call that just a line, or possibly a ray if it continued in one direction. And finally, these 4 line segments do not cross each other. Instead, they meet at points right here, which we call vertices, or the vertex of each side of the shape. So here, even though there's a 4-shaped figure or 4-sided figure here, and they meet at points, the lines cross and continue on. So these lines do cross each other and would not fall into the category of a quadrilateral. So here are our shapes. Which of the figures are quadrilaterals? And we're going to see that they're actually all quadrilaterals. So first, notice that they're all closed. So all of them have an inside and an outside. Okay. So next, they all have 4 line segments as sides. Okay, so you can go through these. I'll save you the time of watching me count, but every single one of these, and a good way to do this is to use a pen. Let's find a weird one. How about this one? Here's 1 side, 2 sides, 3 sides, 4 sides. So we can count the 4 line segments or the sides and check to make sure that there's exactly 4. And you can visually inspect pretty easily whether there's a situation like this, okay, where there's lines that cross. And notice here there's not at every point you see a vertex where the lines do not continue on. So which of the figures are quadrilaterals? And it would be all of them. Now we want to figure out which of these figures are squares. And notice the first requirement for being a square is that you're a quadrilateral. Well, we already know all of these are quadrilaterals, so we don't have to check that. Then we have 2 more requirements, 4 right angles, and the sides all have the same length. Okay. So first, let's see what a right angle is. So a right angle is where 2 line segments meet, and we say they're perpendicular to each other. And sometimes we'll draw this to indicate that something is a right angle. Okay. Just to compare and contrast, oops, I drew one that was a right angle again by accident. This would not be a right angle because it's not straight up and down with respect to each other. This is actually called an acute angle, or if we had something like this, this is more than 90 degrees, which is a right angle. Okay, so again, it's hard to define some of these geometric ideas, but when you look at them, you can see them. Okay, so let's go through and look at all the figures' angles. If they have 4 right angles, we'll keep them. And if they don't, we'll put an X through them so we know they can't be squares. Well, all of these angles are right angles. Okay, so look where the line segments meet at the vertex. This is a right angle, this is a right angle, but these are not, so it doesn't have 4. Okay, this doesn't have any right angles. Looking at these vertices at these points, these are all right angles, so we won't cross that out. No right angles. That almost looks like 1, but regardless, the others are not right angles. Not right angles. Okay, here we have 1 right angle, but the others are not right angles, so that doesn't have 4. Here we don't have 4 right angles, so we'll cross that out. And these also don't have 4 right angles, and J does. Okay, so these 3 shapes all have 4 right angles, okay, and they're all quadrilaterals. But for a square, we need one more requirement. The sides all have to be the same length. Now, looking at these, again, you kind of have to look unless you want to get out a ruler and measure. It appears as if, and in geometry we usually indicate these things, but it appears as if all of these sides are the same length. So I am going to say that A is a square. Now here, these sides are the same length, but notice this side, it's harder to tell, but it's definitely a little bit shorter. So I can kind of think of, if I rotated it down here, they wouldn't be the same length. Okay. So D is not a square. And it's a little bit more obvious with J that these side lengths, they're the same, but they're not the same as these side lengths. So which of the following figures are squares? Well, it's just going to be A. Let's look at the next category. Now we have a rectangle is a quadrilateral with 4 right angles. Well, on the last slide, we already found the 4 that had 4 right angles. It was A, D, and J. Okay. And we said A was the only one that was a square because a square required all of the sides to have the same length. Okay, but rectangles do not require that. So that means these 3 shapes, A, D, and J, are all rectangles. Okay, so notice we said A is a square. A is also a rectangle. So A is a square, and it also meets the definition of a rectangle. However, D and J are rectangles, but they're not squares. So it's sort of like if you live in Phoenix, then you live in Arizona. Okay, but if you live in Arizona, you don't necessarily live in Phoenix. Okay, so A has the property of being both a square and a rectangle. Okay, so all squares are actually rectangles, but all rectangles aren't necessarily squares. Let's look at the next type. A rhombus is a quadrilateral, so we know these are all quadrilaterals, and now we're looking at ones whose sides all have the same length. Okay, so that's all we need. Okay. Well, we know a square, all of the sides are the same length by definition. We already noticed that these ones don't have sides that are all the same length. So now we're going to look at the remaining ones. We know that they're not all right angles, but they could have all sides that are the same length. So now let's cross out the ones that don't meet this requirement. Well, this has short side, longer side, definitely not. Longer side, short side. Okay, these are not all the same length. These are the same length, and these are the same length, but the shorter side is not the same length as the longer side. Okay. These are not all the same length. This is shorter, longer. So these almost look the same, and these almost look the same, but these do not. These sides are actually all the same length. It appears to be the case, so we're not going to cross that out. This side is shorter than this side. This side is longer than this side. So rhombi is plural for rhombus. So we have two figures that are rhombi, which is fun to say, and they are figures 8, which is also a square and a rectangle, and I, which is neither a square or a rectangle, nor a rectangle. Let's look at the next type. Parallelograms are quadrilaterals for which opposite sides are parallel. So we already know they're all quadrilaterals. Let's think about what it means for opposite sides to be parallel. So let's look at the square. Okay, these are opposite sides. They're on the opposite side of the figure. And parallel means that one way to think about it is anywhere you look along this side, the distance from this side to the other side is the same. So this distance is the same as this distance. Okay, and of course you can't check every single distance. That would take the rest of your life and you still wouldn't be finished. But you can eyeball it and you can see that these two lines are parallel. These are opposite sides and they're also parallel. They're equidistant at every point of the side from each other. Okay, so we have one parallelogram. Square seems to be everything. Okay, now these two opposite sides, they are parallel. They're different lengths, but they're still parallel. You see the distance going across. However, these two sides are not. These two sides are opposite, they're not parallel. These two sides are parallel and they're opposite. And we'll mark these with 2. These are opposite sides and they're parallel. So we have another parallelogram. Okay, this does not apply. These are opposite, they're not parallel. Opposite, almost parallel, but nope. Opposite, not parallel. Opposite. Now these are parallel. You might have to look at it a little bit differently, but notice this length is the same here for these opposite sides. And now let's look at the other direction. These are opposite sides, and if you go straight across, they're parallel as well. So we'll circle this one. These, oh, we meant to circle this too. These opposite sides are parallel in both cases, so rectangles are actually parallelograms. And this is what we call our typical parallelogram because it's not any of the other categories like squares or rectangles. The opposite sides are parallel, okay, but it doesn't have any, so these are parallel to each other, but it doesn't have any right angles and the sides aren't the same length. So it's not a square or a rhombus or a rectangle, but it's a parallelogram. Now, these two sides are parallel, but these two sides are not. So this is not a parallelogram. So we have AD, I, J, and K are parallelograms. Okay. And our last category is going to be a trapezoid. Quadrilateral for which at least one pair of opposite sides are parallel. So at least one means one pair exactly, or two pairs of opposite sides are parallel. Okay. Well, notice all parallelograms will be trapezoids because it has two pairs of opposite sides. So AD, I, J, K are all parallelograms. They're quadrilaterals and they have two pairs of opposite sides that are parallel. Now let's look to see if any of these have exactly one pair that's parallel, then they are trapezoids as well. Okay. So I'm noticing this side has, we went through this on the last slide, this has one set of parallel sides. Nope, nope. Looks like this does as well. These sides are parallel. These funky ones, nope. These two sides are parallel. These, none of them are parallel. And these, none of them are parallel. Okay. So our this should say trapezoids. The figures that are trapezoids are A, D, B, I. So let's check them. There's a lot. A, B, D, I, G, J, K, L. G, J, K, and L.